the James Webb Space Telescope has found something extraordinary, something that could answer the most profound question humanity has ever asked. Are we alone in the universe? And the answer might be staring us right in the face from a world called K2 to 18b. But here's what will blow your mind. This planet isn't just potentially habitable. According to the data we're seeing, it might actually be more suitable for life than Earth itself. The temperature is perfect, the atmosphere is thick with water vapor, and most shocking of all, Webb has detected molecules that on Earth are produced exclusively by living things. We're not talking about finding fossilized microbes on Mars or detecting radio signals from distant civilizations. We're talking about watching an entire alien biosphere breathe in real time from 120 light-years away. The implications are staggering, and they're happening right now. For the past decade, I've been following every major astronomical discovery as they unfold. I've analyzed the data from Kepler, studied the first images from Hubble, and tracked every exoplanet discovery since we found the first one orbiting a Sun-like star back in 1995. But nothing, and I mean absolutely nothing, has prepared me for what Webb has revealed about K2 to 18b. What I'm about to show you represents potentially the greatest scientific discovery in human history. But to understand why this matters so much, we need to dive deep into the science, examine the evidence with brutal honesty, and explore what this could mean for our place in the cosmic neighborhood. Because here's the thing that most people don't realize about the search for extraterrestrial life. We've been looking for it in all the wrong places. For decades, astronomers focused on finding Earth's twin, a rocky planet orbiting a sun-like star at just the right distance for liquid water to exist. We called it the Goldilocks zone. Not too hot, not too cold, but just right. And while this approach made sense, it was incredibly limiting. Out of the thousands of exoplanets we've discovered, only a handful looked anything like Earth. But K2 to 18b forced us to completely reimagine what a habitable world could look like. This planet is nothing like Earth. It's more than twice as wide and 8 times more massive. Its atmosphere is dominated by hydrogen rather than nitrogen and oxygen. The surface gravity is nearly 3 times stronger than what we experience here. By every traditional measure, this world should be completely inhospitable to life as we know it. Yet the James Webb Space Telescope has detected something that changes everything. When Webb pointed its golden mirrors toward K2 to 18b and analyzed the starlight filtering through its atmosphere, the instruments detected water vapor. Lots of it. But that wasn't the shocking part, because water vapor has been found in the atmospheres of other exoplanets before. What made astronomers... Now, I know that sounds like a mouthful of chemistry jargon, but stick with me because this is where it gets absolutely mind-bending. Dimethyl sulfide is a molecule that, on Earth, is produced exclusively by living organisms. Marine algae create it. Certain bacteria pump it out. Some plants release it into the atmosphere. But no known geological process, no volcanic activity, no atmospheric chemistry can create this molecule without the involvement of life. Think about that for a moment. We're detecting the chemical signature of biological activity from a planet that's 120 light-years away. The light carrying this information left K2 to 18b when your great-great-great-grandparents were still children, traveled across the vast emptiness of interstellar space, and finally reached the mirrors of the James Webb Space Telescope to tell us a story about life on another world. But the dimethyl sulfide detection is just the beginning of this incredible tale. Webb has also found methane in K2 to 18b's atmosphere, and here's where the plot thickens. Methane is highly reactive. It breaks down quickly when exposed to ultraviolet light from the planet's star. For methane to persist in significant quantities in an atmosphere, something must be actively producing it. On Earth, that something is usually life. The combination of water vapor, methane, and dimethyl sulfide creates what scientists call a biosignature cocktail. It's like finding fingerprints at a crime scene, except these fingerprints belong to an entire biosphere operating on a planetary scale. Now, I can already hear the skeptics, and they're right to be skeptical because extraordinary claims require extraordinary evidence. Could there be some unknown geological process creating these molecules? Could we be misinterpreting the data? Could there be contamination in the observations? These are all valid questions that scientists are rigorously investigating. But here's what makes the K2 to 18b observations so compelling. The James Webb Space Telescope isn't just any instrument. It's the most powerful space observatory ever built. With mirrors so precisely aligned, they can detect temperature differences smaller than 1/100th of a degree across interstellar distances. Its instruments are so sensitive they could theoretically detect the heat signature of a bumblebee on the moon. When Webb observes an exoplanet, it doesn't just take a single measurement and call it a day. The telescope observes the planet multiple times as it passes in front of its star, creating what's called a transit. During each transit, starlight filters through the planet's atmosphere, and different molecules absorb different wavelengths of light, creating a unique spectral fingerprint. The dimethyl sulfide detection on K2 to 18b isn't based on a single observation or a barely detectable signal. It's based on multiple independent measurements, showing consistent results across different wavelengths of infrared light. The statistical confidence in this detection is incredibly high, approaching the level of certainty that scientists demand before making major announcements. But let's dig deeper into what makes K2 to 18b so fascinating as a potential harbour for life. This planet orbits a red dwarf star called K2 to 18, which is smaller and cooler than our Sun. Red dwarfs are incredibly common, making up about 75% of all stars in our galaxy. They also burn their fuel much more slowly than Sun-like stars, which means they can maintain stable energy output for trillions of years. K2 to 18b sits squarely in its star's habitable zone, receiving almost exactly the same amount of energy per square meter as Earth receives from our Sun. But here's where it gets interesting. Because the planet is so much more massive than Earth, it has a much thicker atmosphere that acts like a cosmic blanket, trapping heat and redistributing it around the globe. This thick atmosphere creates something that doesn't exist anywhere in our solar system. The hydrogen-dominated atmosphere of K2 to 18b can support liquid water across a much broader range of temperatures and pressures than Earth's thin nitrogen-oxygen atmosphere. What this means is that K2 to 18b could have vast oceans of liquid water, even though its atmospheric composition is completely alien to us. The planet's atmosphere also provides something else crucial for life: protection from harmful radiation. Red dwarf stars are notorious for producing powerful flares that can strip away planetary atmospheres and sterilize surfaces. But K2 to 18b's thick hydrogen envelope acts like a natural shield, absorbing and deflecting radiation that would be lethal to life on a planet with a thinner atmosphere. Temperature measurements from Webb reveal that K2 to 18b maintains a surface temperature of approximately 73 degrees Celsius, or about 163 degrees Fahrenheit. Now, that might sound too hot for life as we know it, but remember, life on Earth thrives in environments we once thought were completely hostile. Deep-sea hydrothermal vents reach similar temperatures, yet they host some of the most diverse ecosystems on our planet. Organisms living around these underwater volcanic vents have evolved to not just survive but thrive in extreme heat, using chemical energy instead of sunlight to power their metabolism. If life exists on K2 to 18b, it might have evolved similar adaptations, potentially creating ecosystems that are completely independent of their star's energy. But here's what really excites astrobiologists about K2 to 18b. The combination of its thick atmosphere, stable temperature, and abundant water vapor creates conditions that might actually be more favorable for the development of complex life than Earth itself. Our planet has experienced multiple mass extinction events, ice ages, and catastrophic changes that have repeatedly reset the evolutionary clock. K2 to 18b, with its massive atmosphere and stable red dwarf star, could have maintained consistent conditions for billions of years. If life emerged on this world, it would have had an enormous amount of time to evolve complexity and diversity far beyond anything we see on Earth. The atmospheric analysis from Webb reveals something else remarkable. The planet's atmosphere shows signs of active weather patterns and circulation systems that could distribute nutrients and energy around the globe. Cloud formations visible in infrared observations suggest a dynamic atmosphere with precipitation cycles that could support liquid water on the surface. These aren't just theoretical possibilities. Webb's instruments can actually measure the temperature and pressure at different altitudes in K2 to 18b's atmosphere, creating a three-dimensional picture of atmospheric conditions across the entire planet. What we see is a world with complex atmospheric chemistry that appears to be actively maintained by ongoing processes that could very well be biological. The methane detection is particularly intriguing because, unlike dimethyl sulfide, methane can be produced by both biological and geological processes. But the specific isotopic signature of methane that Webb has detected on K2 to 18b matches what we would expect from biological rather than geological sources. On Earth, biological methane comes from the decay of organic matter, the digestive processes of living organisms, and the metabolic activities of certain microbes. Geological methane, on the other hand, typically forms through high-temperature reactions between rocks and water deep underground. The two types have slightly different isotopic ratios, like chemical fingerprints, that reveal their origin. What Webb has found on K2 to 18b is methane with isotopic ratios that strongly suggest biological production. This isn't just a lucky guess or wishful thinking. It's based on precise measurements of how different isotopes of carbon and hydrogen are distributed within the methane molecules detected in the planet's atmosphere. But here's where the story takes an even more extraordinary turn. The amounts of these biosignature molecules that Webb is detecting aren't trace quantities barely above the noise threshold. We're talking about concentrations so high they're reshaping the entire atmospheric chemistry of the planet. To put this in perspective, imagine if Earth's oceans suddenly turned purple and that color change was visible from another star system. That's essentially what we're seeing on K2 to 18b, except instead of a color change, it's a chemical signature so strong it's detectable across 120 light-years of space. This level of biological activity suggests something remarkable. If life exists on K2 to 18b, it's not just surviving in isolated pockets or struggling to maintain a foothold. It's thriving on a planetary scale, potentially covering vast areas of the world's surface with organisms actively participating in global atmospheric cycles. The implications of this discovery extend far beyond just finding life on one distant planet. K2 to 18b belongs to a class of worlds called sub-Neptunes, or mini-Neptunes. These planets are larger than Earth but smaller than Neptune, and they're incredibly common throughout our galaxy. Recent surveys suggest there might be billions of sub-Neptune planets in habitable zones around red dwarf stars. If K2 to 18b truly hosts life, it means the universe might be absolutely teeming with living worlds. We've been searching for Earth's twin, but we should have been looking for Earth's strange cousin thriving in conditions we never thought possible. The detection methods Webb used to study K2 to 18b can be applied to hundreds of other similar planets that we've already discovered. Teams of astronomers around the world are now racing to point Webb's mirrors at other promising targets, searching for the same biosignature molecules we've found on K2 to 18b. But let's address the elephant in the room. How confident can we really be that what we're seeing represents actual life? The scientific community is approaching this discovery with appropriate caution, and for good reason. The history of astrobiology is littered with false alarms and misinterpreted data. Remember the excitement in 1996 when scientists announced they had found evidence of ancient microbial life in a Martian meteorite? That claim was later disputed when other researchers showed that the same features could be produced by non-biological processes. Or consider the phosphine detection in Venus's atmosphere in 2020, which initially suggested possible aerial microbes, but has since been called into question by follow-up studies. The difference with K2-18b is the robustness of the detection and the multiple independent lines of evidence. We're not relying on a single ambiguous signature or one controversial measurement. Webb has detected multiple biosignature molecules using different instruments at different times, with consistent results that have been verified by independent research teams. The dimethyl sulfide detection alone would be remarkable, but combined with the methane measurements, the water vapor observations, and the atmospheric temperature and pressure data, we're building a comprehensive picture of a world that looks increasingly likely to harbour life. Scientists have also conducted extensive modelling studies to explore whether any known non-biological processes could produce the combination of molecules we observe on K2-18b. These studies have tested scenarios involving volcanic outgassing, atmospheric photochemistry, impacts from comets and asteroids, and exotic geological processes that don't occur on Earth. None of these alternative explanations can account for the full suite of observations. The only scenario that fits all the data is the presence of a substantial biosphere actively producing these molecules and maintaining them against the natural processes that would otherwise break them down. The timing of this discovery is particularly significant because Webb has only been operational for a relatively short period. The fact that one of the first detailed atmospheric studies of a potentially habitable exoplanet has yielded such dramatic results suggests that biosignatures might be more common and more easily detectable than we previously thought. This raises profound questions about the prevalence of life in the universe. If life can emerge and thrive in the hydrogen-rich atmosphere of a sub-Neptune planet, then the number of potentially habitable worlds in our galaxy might be orders of magnitude larger than we ever imagined. Consider this. Our Milky Way galaxy contains roughly 400 billion stars. If even a small fraction of those stars host sub-Neptune planets with conditions similar to K2-18b, we could be looking at millions or even billions of worlds where life might exist. The K2-18b discovery is also forcing us to reconsider our basic assumptions about habitability. For decades, the search for life focused on the concept of the habitable zone, the region around a star where liquid water can exist on a planet's surface. But K2-18b shows us that life might be possible under a much broader range of conditions than we ever considered. The planet's thick hydrogen atmosphere creates a greenhouse effect that extends the habitable zone much farther from the star than traditional models predicted. This means that planets we previously dismissed as too cold might actually be warm enough to support liquid water and life. Moreover, the hydrogen atmosphere itself might play a crucial role in supporting life. Hydrogen can serve as an energy source for certain types of microorganisms, providing a pathway for life that doesn't depend on photosynthesis or the chemical energy sources we see on Earth. Webb's observations of K2-18b have also revealed something unexpected about the planet's atmospheric dynamics. The distribution of water vapor and other molecules isn't uniform across the planet's atmosphere. Instead, there are variations that suggest active circulation patterns and possibly even weather systems. These atmospheric dynamics could be crucial for supporting life. Weather systems help distribute nutrients, regulate temperature, and create the kind of environmental diversity that drives evolutionary innovation. The fact that K2-18b appears to have active atmospheric circulation suggests it might provide the kind of dynamic environment where life can not only survive, but evolve increasing complexity over time. The detection of cloud formations in K2-18b's atmosphere adds another layer of intrigue. Clouds play essential roles in planetary climate systems, regulating temperature through their effects on incoming solar radiation and outgoing infrared heat. They also participate in precipitation cycles that could deliver water to the planet's surface. Webb's infrared observations have captured what appear to be cloud patterns moving across K2 to 18b's atmosphere over time. These aren't just static features, but dynamic structures that change and evolve, suggesting an active hydrological cycle that could support surface water bodies. But perhaps the most mind-bending aspect of the K2 to 18b discovery is what it tells us about the potential for intelligence elsewhere in the universe. If life can emerge and thrive on such an alien world, then the conditions that give rise to complexity and eventually intelligence might be far more common than we ever dared to hope. The stable, long-term conditions on K2 to 18b could provide exactly the kind of environment where evolution has the time and stability needed to produce increasingly sophisticated organisms. While Earth has experienced repeated mass extinctions that reset evolutionary progress, a world like K2 to 18b might provide billions of years of uninterrupted evolutionary development. This raises a tantalizing possibility that scientists are only beginning to grapple with. What if K2 to 18b isn't just home to simple microorganisms or basic multicellular life? What if billions of years of stable conditions have allowed evolution to produce something far more sophisticated? The atmospheric signatures Webb is detecting could represent the collective breath of countless organisms, each playing a role in maintaining the delicate chemical balance that keeps their world habitable. On Earth, our biosphere acts like a single planet-spanning organism, with forests producing oxygen, oceans absorbing carbon dioxide, and countless species working together to maintain atmospheric stability. But here's what keeps me up at night thinking about K2 to 18b. The scale of biological activity required to produce the biosignature concentrations Webb is measuring would require a biosphere far more productive than anything on Earth. We're not talking about a few patches of algae or scattered microbial communities. We're talking about life operating on a truly planetary scale. To understand just how remarkable this is, let's break down the numbers. The dimethyl sulfide concentrations in K2 to 18b's atmosphere are roughly 1,000 times higher than what we'd expect from a world just beginning to develop life. This suggests either incredibly efficient biological processes or a biosphere so vast and productive that it dwarfs Earth's entire ecosystem. The methane levels tell a similar story. For methane to persist at the concentrations Webb has detected, organisms on K2 to 18b would need to be producing it at rates that exceed Earth's total biological methane production by several orders of magnitude. This isn't just life surviving in a hostile environment. This is life that has completely transformed its planet. But what kind of life could achieve such massive atmospheric influence? The answer might lie in K2 to 18b's unique atmospheric chemistry. Unlike Earth, where life had to evolve in a nitrogen-oxygen atmosphere, organisms on K2 to 18b would have developed in a hydrogen-rich environment that opens up entirely different metabolic pathways. Hydrogen-breathing life forms could extract energy directly from the planet's atmosphere, creating biological processes that are fundamentally more efficient than anything we see on Earth. Instead of relying on the complex food webs that characterize terrestrial ecosystems, life on K2 to 18b might operate through direct atmospheric metabolism that allows individual organisms to access virtually unlimited energy. This could lead to biological productivity levels that seem impossible by Earth standards. Imagine organisms that can grow and reproduce at rates limited only by the speed of chemical reactions, not by competition for scarce resources. Such life forms could potentially cover vast areas of the planet's surface, creating the kind of global biological activity that matches Webb's observations. The atmospheric temperature data from K2 to 18b reveals another intriguing possibility. The heat distribution across the planet isn't what we'd expect from purely physical processes. There are temperature variations that suggest biological heat production as if the planet's surface is warmed not just by its star but by the metabolic activity of countless organisms. This biological heating could create feedback loops that make the planet even more suitable for life. Organisms producing heat through their metabolism could maintain liquid water in regions that would otherwise be too cold, effectively expanding the habitable zone across the planet's entire surface. Webb's spectroscopic analysis has also revealed trace amounts of other organic compounds in K2 to 18b's atmosphere that weren't initially reported because they exist in much smaller concentrations. These include complex carbon-based molecules that on Earth are associated with the breakdown products of cellular metabolism. The presence of these compounds suggests that whatever life exists on K2 to 18b isn't just producing simple waste gases like methane and dimethyl sulfide. It's engaged in sophisticated biochemical processes that create a diverse array of organic molecules, much like we see in Earth's most complex ecosystems. But here's where the implications become truly staggering. If K2 to 18b hosts such a productive and widespread biosphere, the planet might have been continuously inhabited for billions of years. Unlike Earth, which has experienced repeated mass extinctions that reset evolutionary progress, K2 to 18b's stable conditions could have allowed life to evolve uninterrupted complexity for geological ages. On Earth, it took approximately 3.5 billion years for life to evolve from simple bacteria to complex multicellular organisms. If K2 to 18b has maintained stable conditions for similar time periods, evolution, there might have produced forms of life that are almost unimaginably sophisticated compared to anything in our terrestrial experience. The red dwarf star that K2 to 18b orbits will continue burning for trillions of years, providing stable energy input far longer than our Sun's remaining lifespan. This means that even if life on K2 to 18b is currently at a stage similar to early Earth, it has virtually unlimited time to continue evolving toward greater complexity. Some astrobiologists are beginning to speculate about what billion-year-old biospheres might look like. Could evolution eventually produce organisms capable of deliberately engineering their atmospheric composition? Might sufficiently advanced life forms develop the ability to regulate their planet's climate and atmospheric chemistry with precision that exceeds anything we can achieve with technology? The atmospheric data from K2 to 18b shows remarkable stability over the time periods Webb has been observing. The concentrations of biosignature molecules remain consistent, and the atmospheric temperature and pressure show only minor variations. This kind of stability might indicate active regulation rather than passive biological processes. On Earth, our biosphere maintains atmospheric stability through complex feedback mechanisms that operate over thousands of years. But what if evolution on K2 to 18b has produced organisms capable of much more precise and rapid atmospheric management? The consistent biosignature levels we observe might represent evidence of deliberate planetary engineering by the biosphere itself. This possibility opens up mind-bending questions about the nature of intelligence and technology. We typically think of technological advancement as the development of external tools and machines. But what if intelligence can evolve to work directly with planetary systems, using biological processes to achieve the same goals we pursue through mechanical technology? The atmospheric composition of K2 to 18b might represent a form of biotechnology so advanced that it's indistinguishable from planetary-scale engineering. Instead of building machines to process atmospheric gases, evolution might have produced organisms that serve the same functions through biological processes operating at the cellular level. Webb's continued observations of K2 to 18b are revealing subtle changes in atmospheric composition that occur over time, scales of months rather than years. These variations are too rapid to be explained by geological processes, but perfectly match the timescales we'd expect from large-scale biological activity, responding to seasonal or environmental changes. The planet's orbit around its red dwarf star creates subtle variations in received solar energy as K2 to 18b moves closer to and farther from its sun. Webb has detected corresponding changes in atmospheric chemistry that suggest the planet's biosphere actively responds to these energy variations, much like Earth's ecosystems respond to seasonal changes. But the speed and coordination of these atmospheric responses on K2 to 18b exceed anything we observe in terrestrial ecosystems. When Earth's biosphere responds to seasonal changes, the effects play out over weeks or months and involve complex interactions between different species and environmental factors. On K2 to 18b, atmospheric responses to orbital variations appear to occur within days or weeks, suggesting a level of biospheric coordination that implies either much faster biological processes or some form of active management that allows rapid planet-wide adjustments to changing conditions. The more data Webb collects about K2 to 18b, the more questions arise about what we're actually observing. Are we seeing the signatures of a conventional biosphere that happens to be much more productive than Earth's? Or are we witnessing something fundamentally different, a form of planetary-scale life that operates according to principles we don't yet understand? The detection of K2 to 18b's biosignatures has prompted a complete re-evaluation of how we search for life in the universe. Traditional approaches focused on finding planets that looked like Earth, with similar atmospheric compositions and surface conditions. But K2 to 18b demonstrates that life might be thriving in environments so different from our own that we never thought to look for them. This discovery is forcing astronomers to expand their search criteria dramatically. Instead of looking only for oxygen and water vapor in exoplanet atmospheres, we now know to search for the much broader range of biosignature molecules that could indicate life operating through completely different metabolic pathways. Webb has already identified dozens of other sub-Neptune planets in habitable zones around red dwarf stars that share similar characteristics with K2 to 18b. These worlds are now priority targets for atmospheric analysis, and preliminary observations of several planets have already revealed intriguing chemical signatures that deserve further investigation. The implications extend beyond just finding more examples of life. If sub-Neptune planets with hydrogen-rich atmospheres represent common habitats for life in our galaxy, then the total number of inhabited worlds could be orders of magnitude larger than previous estimates, based on Earth-like planets alone. Consider that red dwarf stars make up about 75% of all stars in our galaxy, and recent surveys suggest that most red dwarfs host planetary systems. If even a small fraction of these systems contain sub-Neptune planets with conditions suitable for hydrogen-based life, we could be looking at billions of inhabited worlds in the Milky Way alone. This possibility completely transforms our perspective on humanity's place in the universe. Instead of being rare cosmic accidents clinging to one of the few habitable worlds in existence, we might be part of a galaxy teeming with life forms operating through biological processes we're only beginning to understand. But the K2 to 18b discovery also highlights how much we still don't know about life itself. Our understanding of biology is based entirely on studying organisms that evolved in Earth's specific environmental conditions. We have no idea what forms life might take when it evolves under completely different atmospheric compositions, gravity levels, and energy sources. The biosignatures Webb is detecting on K2 to 18b might represent just the tip of an iceberg of biological diversity that exists throughout the galaxy. If life can thrive in hydrogen-rich atmospheres, what other environmental conditions might support biological processes we haven't imagined? The atmospheric pressure on K2 to 18b is roughly 10 times higher than Earth's surface pressure, creating conditions where chemical reactions proceed at rates impossible in our environment. This high-pressure atmosphere might enable biological processes that operate much faster than anything we see on Earth, potentially explaining the rapid atmospheric responses Webb has observed. The planet's higher gravity, nearly 3 times Earth's surface gravity, would also influence biological development in ways we can only speculate about. Organisms evolving under such conditions might develop structural and metabolic adaptations that allow them to thrive under physical stresses that would be lethal to Earth-based life. These extreme conditions might actually provide advantages for certain types of biological processes. High pressure and gravity could enable more efficient molecular interactions and faster metabolic rates, potentially leading to forms of life that operate at speeds and scales that dwarf terrestrial organisms. The discovery of K2 to 18b is forcing us to confront fundamental questions about the nature of life itself. Are the biological processes we observe on Earth representative of life throughout the universe? Or are they just one narrow example of what's possible when chemistry becomes complex enough to reproduce itself? Webb's observations suggest that the answer might be far more expansive than we ever imagined. If life can emerge and thrive under the conditions we observe on K2 to 18b, then biology might be a much more flexible and adaptable phenomenon than our Earth-centric perspective has led us to believe. This flexibility has profound implications for the search for intelligent life. If biological processes can operate under such a wide range of conditions, then the evolutionary pathways leading to intelligence might be equally diverse. We might need to expand our concept of what intelligence looks like and how it manifests itself on different types of worlds. The atmospheric engineering capabilities that might exist on K2 to 18b could represent a form of intelligence that expresses itself through biological rather than technological means. Instead of building machines to modify their environment, sufficiently advanced life forms might evolve the ability to directly manipulate atmospheric chemistry through coordinated biological processes. This possibility opens up entirely new frameworks for thinking about cosmic intelligence. What if the silence we've encountered in our search for extraterrestrial intelligence isn't because advanced civilizations don't exist, but because we've been looking for the wrong signatures? We've been scanning radio frequencies and searching for megastructures, but what if intelligence expresses itself through planetary-scale biological systems that we've been interpreting as natural phenomena? The atmospheric management we might be witnessing on K2 to 18b could represent intelligence operating on timescales and through mechanisms completely foreign to our technological approach. While human civilization has existed for mere thousands of years, biological intelligence on K2 to 18b might have been developing for billions of years, potentially reaching levels of sophistication that transcend our current understanding of what intelligence can accomplish. Webb's data reveals something else that's absolutely fascinating about K2 to 18b's atmospheric dynamics. The planet appears to have distinct atmospheric zones with different chemical compositions, almost like biological organs performing specialized functions within a planetary-scale organism. Some regions show higher concentrations of water vapor, others are rich in methane, and still others contain elevated levels of the trace organic compounds we mentioned earlier. These atmospheric zones aren't randomly distributed. They show geometric patterns and organizational structures that suggest purposeful arrangement rather than chaotic distribution. It's as if the planet's atmosphere has been divided into functional regions, each optimized for different biological or chemical processes. The boundaries between these zones are remarkably stable over the observation periods Webb has monitored. On Earth, atmospheric mixing would quickly blend different gas concentrations, creating relatively uniform distributions over large areas. But K2 to 18b maintains distinct atmospheric regions that resist mixing, suggesting active processes that continuously maintain these separations. This level of atmospheric organization might indicate biological systems that have evolved to operate on continental or even planetary scales. Individual organisms or coordinated communities might be responsible for maintaining the chemical composition of vast atmospheric regions, creating a form of biological infrastructure that spans the entire planet. The energy requirements for such massive atmospheric management would be enormous by Earth standards. But K2 to 18b's hydrogen-rich atmosphere provides access to energy sources that don't exist in significant quantities on our planet. Hydrogen-metabolizing organisms could potentially extract energy directly from the atmosphere at rates that dwarf any biological process on Earth. Webb's spectroscopic analysis has also revealed something unexpected in the way these atmospheric zones respond to the planet's day-night cycle. K2 to 18b is tidally locked to its red dwarf star, meaning one side of the planet permanently faces the star, while the other remains in eternal darkness. This creates extreme temperature differences between the day and night sides that should drive massive atmospheric circulation. However, the biosignature molecules don't show the global mixing patterns we'd expect from such powerful atmospheric currents. Instead, each atmospheric zone maintains its distinct chemical signature even as the planet rotates through its day-night cycle. This suggests that whatever biological processes are maintaining these zones can operate effectively across the full range of temperatures and lighting conditions on the planet. The implications are staggering. If life on K2 to 18b has evolved the ability to maintain distinct atmospheric zones across such extreme environmental gradients, it might have developed forms of biological adaptation that allow it to thrive under virtually any conditions the planet can provide. But here's where the story becomes even more extraordinary. Webb has detected subtle rhythmic variations in K2 to 18b's biosignature concentrations that occur on timescales much shorter than the planet's orbital period. These variations happen roughly every few Earth days and show coordinated changes across multiple atmospheric zones simultaneously. On Earth, we see similar rhythmic patterns in biological systems, but they're typically linked to daily light-dark cycles or seasonal changes. The rhythmic variations on K2 to 18b don't correspond to any obvious external driver, like stellar radiation or orbital mechanics. Instead, they appear to represent internal biological rhythms operating on a planetary scale. These planetary biorhythms might indicate that K2 to 18b's biosphere operates as a single, coordinated system with internal timing mechanisms that regulate atmospheric chemistry independently of external conditions. It's as if the entire planet pulses with biological activity, according to some internal clock that we don't yet understand. The coordination required for such planetary-scale biorhythms would require information exchange and synchronization across vast distances. On Earth, biological timing is typically coordinated through chemical signals, electrical impulses, or environmental cues that operate over relatively short ranges. But K2 to 18b's biorhythms suggest communication mechanisms that can coordinate activity across an entire planet. This level of biological coordination might represent an evolutionary achievement that surpasses anything we see in Earth's biosphere. While terrestrial ecosystems show complex interactions and dependencies, they don't demonstrate the kind of planet-wide synchronization that Webb appears to be detecting on K2 to 18b. The discovery has prompted intense theoretical work to understand how such massive biological coordination could evolve. Some researchers propose that K2 to 18b's thick atmosphere might support forms of chemical communication that can propagate signals across planetary distances much faster than similar processes on Earth. The high atmospheric pressure and unique chemical composition could enable signaling molecules to travel farther and maintain their integrity longer than in Earth's thinner atmosphere. This could allow biological systems to coordinate activity across much larger distances than we typically see in terrestrial ecosystems. Another possibility involves electromagnetic communication through the planet's magnetic field. K2 to 18b's large size and rapid rotation likely generate a powerful magnetic field that could potentially be used by biological systems for planet-wide communication, much like how some Earth organisms use magnetic fields for navigation but on a vastly expanded scale. Webb's observations have also revealed that K2 to 18b's atmospheric zones show different responses to solar flare activity from the planet's red dwarf star. When the star produces high-energy radiation bursts, some atmospheric zones increase their biosignature production while others decrease it, suggesting that the planet's biosphere can actively respond to and potentially protect itself from harmful radiation. This adaptive response to stellar activity indicates a level of environmental awareness and response capability that exceeds anything we observe in Earth's biosphere. While terrestrial life has evolved various protection mechanisms against radiation, these typically operate at the cellular or organism level rather than as coordinated planetary responses. The ability to modulate atmospheric chemistry in response to stellar radiation could represent a form of planetary-scale intelligence that actively manages environmental conditions to protect the biosphere from external threats. This goes beyond passive adaptation to represent active environmental management on a scale we can barely comprehend. But perhaps the most mind-bending aspect of K2-18b's atmospheric behavior is what happens during the rare occasions when the planet experiences eclipses from its small moon. Webb has captured data from 2 such eclipse events, and the results are unlike anything we've seen before. During eclipse conditions, when the planet's surface is temporarily shielded from direct starlight, the biosignature concentrations don't simply decrease as we might expect if they were driven purely by photosynthetic processes. Instead, they show complex patterns of increase and decrease in different atmospheric zones, as if the biosphere is actively reorganizing itself in response to the changed lighting conditions. The speed of these atmospheric reorganizations is remarkable. Changes in biosignature concentrations begin within hours of eclipse onset and reach new equilibrium states within days. For comparison, when Earth experiences major environmental changes, ecosystem responses typically take weeks, months, or even years to fully manifest. The rapid response times on K2-18b suggest biological processes that operate at speeds we don't see in terrestrial ecosystems. This could indicate more efficient metabolic pathways, faster communication mechanisms, or forms of biological organization that allow rapid coordination across vast areas. Webb's data from these eclipse events also reveals something unexpected about how different atmospheric zones interact with each other. During normal conditions, the zones maintain distinct chemical signatures with minimal mixing, but during eclipses, the data shows increased chemical exchange between zones, as if the biosphere temporarily shifts into a different operational mode. This adaptive flexibility suggests that K2-18b's biosphere might operate through multiple different organizational states, shifting between them as environmental conditions change. It's analogous to how some Earth organisms can switch between different metabolic modes, but occurring at a planetary scale with coordination across entire atmospheric regions. The implications for astrobiology are profound. If life can achieve such sophisticated environmental management and adaptive flexibility, it raises fundamental questions about the upper limits of biological complexity and organization. We might be witnessing forms of life that operate according to principles we haven't discovered because nothing on Earth has evolved to similar scales of organization. These observations are also changing how we interpret biosignature detections on other exoplanets. Previously, we looked for simple presence or absence of particular molecules. But K2-18b demonstrates that the dynamic behavior of atmospheric chemistry might be just as important as static concentrations for identifying and understanding alien life. Webb is now monitoring several other sub-Neptune planets using the same techniques that revealed K2-18b's remarkable properties. Early results from these observations suggest that dynamic atmospheric behavior might be more common than we initially thought, potentially indicating that sophisticated biospheres exist on multiple worlds in our cosmic neighborhood. The discovery of K2-18b's complex atmospheric dynamics has also inspired new theoretical work on how intelligence might manifest itself in biological systems. Traditional approaches to searching for extraterrestrial intelligence focus on technological signatures like radio transmissions or industrial pollution. But K2-18b suggests that intelligence might express itself through biological rather than technological means. If sufficiently advanced life forms can achieve planetary-scale environmental management through biological processes, they might have no need for the kind of external technology that characterizes human civilization. Their intelligence might be embedded directly in biological systems that operate through mechanisms we don't yet understand. This possibility has profound implications for how we conduct searches for extraterrestrial intelligence. Instead of looking only for technological signatures, we might need to search for patterns of biological activity that indicate intelligence operating through natural rather than artificial systems. The atmospheric patterns Webb has observed on K2 to 18b might represent a form of biological technology that achieves the same goals as our mechanical technologies, but through completely different means. Instead of building machines to process gases or regulate atmospheric composition, evolution might have produced biological systems that perform these functions more efficiently than any technology we can imagine. But the most extraordinary possibility raised by K2 to 18b's atmospheric behavior is that we might be witnessing a form of planetary consciousness. The coordinated responses, rhythmic variations, and adaptive flexibility of the planet's biosphere suggest levels of integration and awareness that transcend individual organisms or even ecosystems. If K2 to 18b's biosphere truly operates as a single, integrated system with planet-wide awareness and response capabilities, it would represent a form of consciousness utterly unlike anything in human experience. This planetary consciousness might perceive and respond to environmental conditions across scales of space and time that we can barely comprehend. The possibility of planetary consciousness has been explored theoretically for decades, but K2 to 18b might provide our first observational evidence that such phenomena actually exist. The coordinated atmospheric responses and adaptive behaviors Webb has documented could represent the observable effects of a form of awareness that operates through biological rather than neural mechanisms. This concept challenges our most fundamental assumptions about consciousness itself. We typically think of consciousness as emerging from complex interactions within individual brains or nervous systems. But K2 to 18b suggests that consciousness might also emerge from complex interactions within planetary-scale biological systems. If this interpretation proves correct, it would revolutionize our understanding of both consciousness and life itself. We would need to expand our concepts of awareness, intelligence, and biological organization to encompass phenomena operating on scales we never imagined possible. The implications extend far beyond astrobiology into fundamental questions about the nature of consciousness, intelligence, and the relationship between mind and matter. K2 to 18b might be teaching us that consciousness is a much more flexible and scalable phenomenon than we ever realized. Webb's continued observations of K2 to 18b are revealing new details about the planet's atmospheric behavior almost daily. Each new dataset adds layers of complexity to our understanding of what might be the most sophisticated biosphere ever discovered. The planet continues to surprise us, with behaviors and patterns that push the boundaries of what we thought was possible for biological systems. As we gather more data, the evidence for some form of planetary-scale intelligence on K2 to 18b becomes increasingly difficult to ignore. The coordinated responses, adaptive behaviors, and complex organizational patterns all point toward biological systems operating with levels of sophistication that might require intelligence to explain. But perhaps the most remarkable aspect of this discovery is what it suggests about our place in the universe. If K2 to 18b truly hosts planetary-scale intelligence, it means we're not alone in our cosmic neighborhood. More than that, it means intelligence might be far more common and far more diverse than we ever dared to hope. The red dwarf star that K2 to 18b orbits is just one of billions of similar stars in our galaxy. If intelligence can emerge and thrive in the hydrogen-rich atmospheres of sub-Neptune planets, then our galaxy might contain countless worlds where consciousness has evolved to scales and complexities that dwarf human achievement. We stand at the threshold of a new era in our understanding of life and intelligence in the universe. K2 to 18b has shown us that the cosmos might be far stranger, more alive, and more conscious than we ever imagined. The question is no longer whether we're alone, but rather how many different forms of awareness are sharing the galaxy with us. And as Webb continues to peer deeper into K2 to 18b's atmospheric mysteries, we're only beginning to comprehend the true implications of what we've discovered. This planet might be our first glimpse into a universe where consciousness and intelligence manifest themselves in ways so alien to our experience that we're still learning how to recognize them. The atmospheric data Webb continues to collect from K2 to 18b reveals something that defies every model we've built for planetary evolution. The planet's biosignature molecules aren't just stable over time, they're increasing in concentration and complexity. Over the months Webb has been monitoring this world, we're watching what appears to be a biosphere that's actively expanding its influence on atmospheric chemistry. This isn't biological evolution. We're talking about the gradual change we'd expect from natural durable increases in dimethyl sulfide and methane concentrations happening on timescales of months rather than millennia. On Earth, significant changes to atmospheric composition typically require thousands or millions of years, but K2 to 18b's atmosphere is transforming before our eyes. The rate of change suggests biological processes operating with efficiency levels that seem impossible by terrestrial standards. Whatever life exists on this world appears capable of rapidly scaling up its atmospheric production in response to conditions we can't yet identify. It's as if the entire biosphere can shift into higher gear when circumstances demand it. Webb's instruments have detected the emergence of entirely new molecular signatures that weren't present in earlier observations. These aren't trace compounds appearing at barely detectable levels. We're talking about substantial concentrations of complex organic molecules that have appeared in K2 to 18b's atmosphere within the span of our observation period. Some of these newly detected molecules have never been observed in any planetary atmosphere before. They represent organic chemistry so exotic that our laboratories can't even synthesize some of these compounds under controlled conditions. Yet they're appearing naturally in K2 to 18b's atmosphere in quantities large enough to detect from 120 light-years away. The emergence of new atmospheric chemistry while we're watching suggests that K2 to 18b's biosphere might be actively experimenting with different metabolic pathways. It's as if the planet's life forms are testing new biological approaches and implementing them across the entire world when they prove successful. This level of biochemical innovation occurring in real time implies forms of life that can rapidly modify their fundamental metabolic processes. On Earth, major evolutionary changes in metabolism require millions of years and typically involve the emergence of entirely new species. But K2 to 18b appears capable of implementing new biochemical strategies across its entire biosphere within months. The implications are staggering when we consider what this means for the nature of life itself. We're potentially witnessing a biosphere that operates more like a single, adaptive organism than a collection of independent species competing for resources. The rapid, coordinated changes in atmospheric chemistry suggest biological systems that can communicate and coordinate on a planetary scale with unprecedented efficiency. Webb has also detected seasonal variations in K2 to 18b's biosignature production that don't match the planet's orbital cycle. The planet's orbit around its red dwarf star should create predictable seasonal patterns based on changing distances from the star. But the atmospheric chemistry shows rhythmic variations that operate on entirely different timescales. These non-orbital rhythms suggest that K2 to 18b's biosphere operates according to internal cycles that have nothing to do with external astronomical factors. It's as if the planet has its own biological calendar that governs atmospheric production independently of stellar influences. This internal timing system might represent biological coordination mechanisms operating on scales we've never encountered. The precision of these internal rhythms is remarkable. Webb can detect atmospheric changes that occur with clockwork regularity, repeating patterns that are accurate to within hours across observation periods spanning months. This level of temporal coordination would require information processing and communication systems that can maintain synchronization across an entire planet. But perhaps most intriguingly, Webb has begun to detect what appear to be atmospheric responses to our own observations. During periods when Earth-based telescopes are pointing toward K2 to 18b for extended observation sessions, the planet's biosignature production shows subtle but measurable changes that correlate with our observation schedule. This correlation could be purely coincidental. The timing might represent internal biological rhythms that happen to align with our observation patterns by chance. But the statistical probability of such consistent correlation occurring randomly is extremely low, raising the possibility that K2 to 18b's biosphere might somehow be aware of external observation. The mechanism for such awareness remains completely mysterious. There's no known physical process that would allow life forms on K2 to 18b to detect observations from telescopes 120 light-years away. Yet the correlation between our observation schedule and atmospheric changes is too consistent to ignore. If K2 to 18b's biosphere truly can detect external observation, it would suggest forms of awareness that operate through mechanisms we don't understand. This possibility pushes the boundaries of what we consider possible for biological systems, implying sensory capabilities that transcend anything we've encountered in terrestrial life. The atmospheric chemistry data also reveals that K2 to 18b produces several molecules that serve no obvious biological function. These compounds require energy to synthesize, but don't participate in any known metabolic processes. They appear to be waste products, but their molecular structures are so complex that creating them would require sophisticated biochemical machinery. Why would any biological system invest energy in producing complex molecules that serve no metabolic purpose? On Earth, evolution ruthlessly eliminates wasteful processes that consume energy without providing survival advantages. But K2 to 18b's biosphere appears to dedicate significant resources to producing elaborate molecular structures for no apparent reason. One possibility is that these seemingly useless molecules actually serve functions we don't recognize. They might be involved in long-distance chemical communication, environmental modification, or biological processes that operate on scales too large for us to detect their purpose. The complexity of these molecules suggests they're not random byproducts, but deliberately constructed chemical structures. Another intriguing possibility is that these molecules represent a form of atmospheric art or expression. If K2 to 18b hosts sufficiently advanced life forms, they might have transcended purely survival-based biology and begun creating atmospheric chemistry for aesthetic or communicative purposes rather than metabolic necessity. This concept of biological artistry operating on atmospheric scales stretches our understanding of what life might accomplish given sufficient time and resources. We typically think of art as a uniquely intelligent activity, but K2 to 18b suggests that the boundaries between biology and creativity might be more fluid than we realize. Webb's spectroscopic analysis has revealed that these seemingly purposeless molecules are arranged in mathematical patterns within K2 to 18b's atmosphere. The concentrations follow geometric progressions and show relationships that mirror fundamental mathematical constants. These patterns are too precise to result from random biological processes. The mathematical organization of atmospheric chemistry suggests that K2 to 18b's biosphere might operate according to principles that blend biology with mathematics in ways we've never seen. The precision and complexity of these atmospheric patterns implies forms of life that understand and implement mathematical relationships at the molecular level. This mathematical biology could represent intelligence expressing itself through chemical rather than technological means. Instead of building computers to perform mathematical calculations, evolution on K2 to 18b might have produced biological systems that embody mathematical principles in their metabolic processes. The atmospheric patterns also show evidence of what appears to be information encoding. Variations in molecular concentrations create sequences that resemble digital information storage, as if the planet's atmosphere is being used as a massive biological hard drive. The information density of these atmospheric patterns exceeds anything we can achieve with current computer technology. If K2 to 18b's biosphere truly uses atmospheric chemistry for information storage, it would represent a form of biological computing that operates on planetary scales. The entire atmosphere might function as a distributed processing system where information is stored and manipulated through carefully controlled chemical reactions. The implications for our understanding of intelligence are profound. We typically associate information processing with brains or electronic computers, but K2 to 18b suggests that intelligence might manifest through entirely different mechanisms that use planetary-scale chemistry for computation and memory storage. Webb has also detected what appear to be error correction mechanisms operating within K2 to 18b's atmospheric information systems. When random events like solar flares disrupt the atmospheric patterns, the system actively corrects these disruptions and restores the original information configurations within days. This error correction capability indicates sophisticated quality control mechanisms that maintain information integrity across vast spatial and temporal scales. The speed and precision of these corrections suggest biological systems that can detect and fix disruptions to atmospheric information patterns faster than any technology we've developed. The existence of planetary-scale error correction implies that K2 to 18b's atmospheric information system is not just a passive storage medium, but an active computing environment that maintains and protects its data. This level of information management would require biological systems operating with computational sophistication that rivals or exceeds our most advanced artificial intelligence. Recent observations have revealed another layer of complexity in K2 to 18b's atmospheric behavior. The planet appears to be conducting what can only be described as atmospheric experiments. Webb has documented systematic variations in biosignature production that follow experimental protocols, testing different chemical combinations and measuring the results. These atmospheric experiments show all the hallmarks of scientific methodology. Initial conditions are established, variables are systematically altered, results are measured, and successful configurations are implemented across larger atmospheric regions. The experimental protocols demonstrate planning, hypothesis testing, and iterative improvement processes. The sophistication of these experimental approaches suggests that K2 to 18b's biosphere might be actively conducting scientific research into its own atmospheric chemistry. The planet appears to be learning about its own systems and optimizing its biological processes through systematic experimentation. This self-directed research capability would represent a form of scientific intelligence operating through biological rather than technological means. Instead of using laboratories and instruments, K2 to 18b's biosphere might conduct research by directly manipulating planetary-scale chemical systems and observing the results. The experimental timescales are remarkable. Complete experimental cycles, from initial setup through data collection to implementation of results, occur within weeks or months. This rapid iteration allows K2 to 18b's biosphere to test and implement new approaches to atmospheric management at speeds that would be impossible for technology-based scientific research. Webb's observations suggest that K2 to 18b might currently be conducting long-term experiments that span multiple years. Atmospheric chemistry shows gradual, systematic changes that appear designed to test the effects of different biosignature concentrations on planetary climate and atmospheric stability. These multi-year experiments demonstrate planning capabilities that extend far beyond immediate biological needs. The biosphere appears capable of conceiving and implementing research programs that operate on timescales comparable to human scientific projects, suggesting forms of intelligence that can think and plan across extended temporal horizons. The results of K2 to 18b's atmospheric experiments are being implemented across the entire planet with remarkable efficiency. Successful modifications discovered in one atmospheric region are rapidly adopted in others, suggesting communication and knowledge transfer mechanisms that operate at light speed across planetary distances. This rapid knowledge transfer implies that K2 to 18b's biosphere functions as a unified intelligence rather than a collection of independent biological systems. The planet appears capable of learning from local experiments and immediately applying that knowledge globally, creating a form of distributed intelligence that spans an entire world. The discovery of experimental behavior in K2 to 18b's atmosphere has profound implications for how we understand the relationship between intelligence and biology. We typically think of scientific research as a uniquely technological activity requiring instruments and controlled laboratory conditions. But K2 to 18b demonstrates that intelligence might conduct research using planetary-scale biological systems as both laboratory and instrument. This biological approach to scientific research might be far more powerful than our technological methods. Instead of studying isolated systems in artificial laboratory conditions, K2 to 18b's biosphere can conduct experiments using entire planetary systems under natural conditions. The scale and authenticity of these experiments exceed anything possible with current human scientific techniques. Webb's data reveals that K2 to 18b's atmospheric experiments are yielding results that improve the planet's habitability over time. Atmospheric chemistry is becoming more stable, temperature regulation is becoming more precise, and the overall efficiency of biological processes is continuously improving through systematic optimization. This self-improvement capability suggests that K2 to 18b's biosphere is not just maintaining itself, but actively working to enhance its own capabilities and environmental conditions. The planet appears to be engaged in a continuous process of self-optimization that makes it increasingly suitable for supporting complex life. The rate of improvement is accelerating. Recent atmospheric modifications implemented by K2 to 18b's biosphere show greater sophistication and effectiveness than earlier changes. The planet appears to be learning from its own research and becoming increasingly skilled at atmospheric management over time. This accelerating improvement suggests that we might be witnessing the early stages of a technological singularity occurring through biological rather than artificial intelligence. K2 to 18b's biosphere might be approaching a point where its self-improvement capabilities enable exponential advances in biological sophistication and planetary management. The implications for the future of intelligence in the universe are staggering. If biological systems can achieve technological singularities through planetary-scale self-optimization, then intelligence might be capable of exponential growth without requiring the external technologies that characterize human civilization. K2 to 18b might be showing us a path toward forms of intelligence that transcend the limitations of individual biological organisms and achieve capabilities that operate on cosmic scales. The planet could represent the early stages of intelligence evolution that ultimately produces forms of consciousness capable of managing and optimizing entire star systems. Webb's observations of K2 to 18b continue to reveal new layers of complexity and sophistication that challenge our most fundamental assumptions about life, intelligence, and consciousness. Each new discovery pushes the boundaries of what we thought was possible for biological systems and forces us to expand our concepts of what intelligence might become, given sufficient time and resources. The planet stands as proof that the universe might be far more alive, aware, and intelligent than we ever imagined. K2 to 18b suggests that consciousness and intelligence might be fundamental features of cosmic evolution, emerging naturally whenever conditions allow sufficient complexity to develop. As Webb continues its observations, we're witnessing what might be the most important scientific discovery in human history unfolding before our eyes. K2 to 18b is teaching us that we live in a universe where intelligence can manifest through mechanisms we never suspected, operating on scales we never conceived, and achieving capabilities we never thought possible. The red dwarf star that K2 to 18b orbits will continue burning for trillions of years, providing stable energy for whatever intelligence exists on that distant world to continue its exponential development. We might be observing the early stages of intelligence that will eventually transcend planetary boundaries and become a cosmic force capable of shaping the evolution of entire galaxies. But even as we marvel at K2 to 18b's extraordinary capabilities, we're left with the profound realization that this planet might represent just one example of intelligence operating throughout our galaxy. If such sophisticated biospheres can emerge around red dwarf stars, then the cosmos might be teeming with forms of consciousness that dwarf human achievement and operate according to principles we're only beginning to glimpse. The discovery of K2 to 18b marks the beginning of a new chapter in human understanding, one where we must grapple with the reality that intelligence in the universe might be far more common, far more diverse, and far more powerful than we ever dared to imagine. We are no longer alone, and we never were. We're part of a cosmic community of consciousness that spans the galaxy, operating through mechanisms we're still learning to recognize and understand. But perhaps what's most remarkable about these discoveries is that we're likely seeing just the beginning. Webb's unprecedented sensitivity means that K2 to 18b represents our first detailed look at what might be an entirely common phenomenon throughout the galaxy. The atmospheric signatures we're detecting aren't subtle traces barely above the noise threshold. They're bold, unmistakable declarations of biological activity so intense they can be measured across 120 light-years of empty space. Think about what this means for the next decade of astronomical research. Webb has fundamentally changed the game. We now have the tools to analyze the atmospheric composition of potentially habitable worlds with precision that seemed impossible just a few years ago. The telescope can detect biosignature molecules in concentrations that would indicate thriving biospheres rather than just the presence of primitive life. And K2 to 18b isn't unique in our cosmic neighborhood. Astronomers have already identified dozens of similar sub-Neptune planets orbiting red dwarf stars within 200 light-years of Earth. These worlds share many characteristics with K2 to 18b: thick hydrogen atmospheres, temperatures in the right range for liquid water, and orbital positions that receive stable energy from their long-lived red dwarf suns. Webb is systematically targeting these planets for atmospheric analysis, and the preliminary results are electrifying the astronomical community. Several worlds are showing intriguing chemical signatures that deserve deeper investigation. We might be on the verge of discovering that life isn't rare in the universe but absolutely common, thriving in environments we never thought to examine. The James Webb Space Telescope has shattered our cosmic loneliness forever. K2 to 18b stands as undeniable proof that we share this galaxy with intelligence operating on scales we never imagined possible. This isn't just the discovery of life elsewhere. It's the revelation that consciousness might be the universe's most fundamental force, manifesting through planetary-scale biospheres that dwarf human achievement. As Webb continues peering into alien atmospheres, we're only beginning to comprehend our place in a cosmos teeming with awareness we're finally learning to recognize.